lecture number 5 for the chapter Principle of Mathematical Induction, class 11. In the previous lectures, we have discussed up to question number 16. Now we'll discuss the question number 17, which says that the statement is equal to n upon 3 to n plus 3. So let it equal to Pn, and we prove that it is true for n is equal to 1. So for n is equal to means 1 means that the sum of one term in the left hand side is equal to 1 upon 15, and in right hand side, if you replace n by 1 here, you will get 1 upon 15. So both are equal to each other. So we can say that this statement is true for n is equal to 1. Now we'll prove that we learned that it is true for any natural number n. So Pm will be equal to 1 upon 3 into 5, 1 upon 5 into 7, up to 1 upon 3, 2 into m plus 1 into 2 and m plus 3. And m upon 3, 2 m plus 3, that is, you have to replace n by m in the left hand side and as well as in the right hand side. Now to prove that it is true for n is equal to m plus 1, you have to add the next term of this to the left hand side as well as the right hand side. So what will be the next term of this? It will be 2m plus 1 plus 1, 2m plus 1 plus 3. This is the next term of this. You have to add this to the left hand side as well as in the right hand side. You have to prove it. So simplified the right hand side, simplify the right hand side. So this is 1 upon this, open the bracket, this will be this, and it is common. 1 upon 2 m plus 3 is common. So m upon 3 plus 1 upon 2 m plus 5, add these two, factorize the numerator. On factorizing you are getting this. So which term will be cancelled out? 2m plus 3 will cancel out 2m plus 3, and we are getting m plus 1 upon 2m plus 5 plus 3. For in place of 2m plus 5, you can write 2m plus 1 plus 3. When you open this bracket, it will be equal to this, because you have to prove that this will be the next term of this. That is the sum for the m terms. So the sum for m plus 1 will be m plus 1 upon 3, 2m plus 1 plus 3. This is the next term. So it is true for n is equal to m plus 1 whenever it is true for n is equal to m. Therefore, by PMI, Pn is true for all natural numbers. So this is the question number 17. In question number 18, in place of equal sign, we have this less than sign. So we proceed as usual. It is 1 plus 2 plus 3 up to n. The sum of these terms is less than 1 upon 8 to n plus 1. So for n is equal to 1, the term of one term is equal to 1. And in the right hand side, we have 1 upon 8, 2 into 1 plus 1. That is 1 upon, that is, if you simplify it, you are getting 2 plus 1, 3, 3 square 9, 9 upon 8, which is greater than 1. Right hand side is greater than 1. So it means it is true for n is equal to 1. Now let us true for the statement is true for n is equal to m. So 1 plus 2 plus 3 up to m is less than 1 upon 8 to m plus 1 whole square. This is the this is not the power, this is 2m. This is 2m. Now as usual, we add the next term of the left hand side, that is m is the mth term. The next term will be m plus 1. So you have to add this m plus 1 on both sides. And on adding the right hand side with the inequality sign, we should obtain the next term of this, which will be 2m plus 1 whole square. So on adding, simplifying the right hand side, adding by taking the LCM, it will be 8m plus 8 whole square of it. Factorize this, which is rather 2m plus 3 whole square. 2m square plus 12m plus 9, it is a whole square of 2m plus 3. For 2m plus 3, you can write 2m plus 1 because this is a simplified form of this and whole square is there. So it is the next term of this. So we can prove, we have proved that this is true for n is equal to m plus 1 whenever it is true for n is equal to m. So therefore by PMI it is true for all natural numbers. Now question number 24, you have to prove that this statement is less than this statement for all natural number. So this question is somewhat different from the above. So we prove that it is true for n is equal to 1. To put 1 in the left hand side, 1 in the right hand side. For n is equal to 1, the left hand side is 2 into 1 plus 7. In the right hand side, it is 1 plus 3 whole square. So 9 less than 16, which is true for n is equal to 1. Now we let that it is true for n is equal to m. So simply you have to replace n by m in the left hand side, m by m in the right hand side. Now what do you have to prove? You have to prove that it is true for n is equal to m plus 1. It means in the left hand side you should obtain 2m plus 1 plus 7. In the right hand side you should obtain m plus 4 whole square. So what I've done, this is the somewhat different question from the above. Because I need 2m plus 1 plus 7 in the left hand side, so I've added 2 on both sides. 2 plus here, 2 plus here. Simple arrangement is there. Adding 2 on both sides. So you can take 2 common in these two terms, which is 2m plus 1 plus 7. And this is the next term of the left hand side. Now in the right hand side we have added 2. So it comes out to be m square plus 9 plus 6m plus 2. Now what I have done, I have added 5 plus 2m on the right hand side only. I have added 5 plus 2m in the right hand side only. Why? Because right hand side is greater, and if we add something to a greater value, it will remain greater. It will remain greater. If we add something to a greater value, it will remain greater. In this step, I have added only 2 to both sides. The statement will be true. Now because in the left hand side we had obtained the next term of this m, 2m plus 7, that is 2m plus 1 plus 7. In the right hand side we need m plus 4 whole square. So I have added 5 plus 2m on the right hand side so that it will be m plus 4 whole square. I have arranged it because I need m plus 4 whole square. It means I need m square. I need 16. So I have 9 and 2 11. So I need 5. So I have added 5. I need 8m, and because I have 6m, so I have added 2m so that it become 8m. So that is why I have added 5 plus 2m in the right hand side, and by adding something to a greater value, it will remain greater. So it is true for n is equal to m plus 1 whenever it is true for n is equal to m. So this is the question number 24, which is somewhat different from the above questions we have done. Now from question number 20 onwards, or rather 19 onwards, there are second types of question like this. You have to prove that 10 raised to power 2n minus 1 is divisible by 11. You have to prove it. That's this statement, 10 raised to power 2n minus 1 is divisible by 11. You have to prove it. So we don't have the series on the left hand side. We have only the statement 10 raised to power 2n minus 1, and you have to prove that this statement is divisible by 11 for all natural number. For all natural number you have to prove it. So as usual, you let that it is equal to Pn. Now for n is equal to 1, replace n by 1. So 10 raised to power 2 into 1 minus 1 is coming out to be 11, which is divisible by 11. So it means P1 is divisible by 11 for n is equal to 1. Now let that it is true for n is equal to any natural number m. So Pm will be equal to 10 raised to power 2m minus 1 plus 1. And because we have let that it is true for n is equal to m, so Pm will be divisible by 11. We have let that it is true for n is equal to m, means this expression will be divisible by 11. We have let it. So because we have let it is divisible by 11, so let this statement equal to 11m, because it is divisible by 11. So 10 raised to power 2m minus 1 is equal to 11k minus 1. This is the value of 10 raised to power 2m minus 1, 11k minus 1. Now I have to prove that it is true for n is equal to m plus 1. So simply replace m by m plus 1 in the right hand side. This will be Pm plus 1, and I'll prove that this statement is divisible by 11. I have to prove it that it is true for n is equal to m plus 1, that is Pm plus 1 is divisible by 11. Now see the arrangement here. So 10 raised to power 2m plus 2 minus 1, and I break like this, 10 raised to power 2m minus 1 and 10 raised to power 2. I break it like this. Why I break like this? Because I know the value of this, 10 raised to power 2m minus 1. I know this. I've let it here 11k minus 1. So 10 raised to power 2m minus 1, I put it here. 10 raised to power 2, I have put it here. Simple arrangement is here. Now the value of 10 raised to power 2m minus 1 is equal to 11k minus 1. To replace the value of this as 11k minus 1, open the bracket, and you are getting 11 common in both the terms because this is 100, open the bracket, minus 100 plus 1 will be equal to 99, and you can take easily 11 common, which is divisible by 11. So Pn plus 1 expression is this, which is divisible by 11. So we can say that this statement is true for n is equal to m plus 1 whenever it is true for n is equal to m. And therefore, this Pn is divisible by 11 for all natural number. Pn is divisible by 11 for all natural numbers. So this is the question number 20 or 19. We'll discuss it later on. And this is the second types of question in which you have to prove that the given statement is either multiple or divisible by some number, or it is a factor of some other expression or statement. We'll discuss the remaining question in the next lecture. Thank you.